All right, so last time we talked about the differential gene expression, right? That's the first topic we have been talking about so far. And in the last lecture specifically, we were talking about the case of doing the two sample t-test, but the sample sizes M and N are too small. So we were saying that the issue is with using the pooled sample variance to estimate sigma square. So the pooled sample variance we denoted by SP square, and the common variance, sorry, let me see what happens here. And the common sample variance is denoted by sigma square. So we are saying that when the sample size is, oops, trying to enlarge the screen. Just give me a second. How can I make it full screen? Okay. So this issue we're saying is that when the sample sizes M and N are too small, and we know that under this two Gaussian normal distributions assumption, this SP square would follow this chi-square distribution. And based on this, we can tell that the variance of this term, SP square, would actually be inversely proportional to this n plus n minus 2. So therefore, the smaller the sample size, the bigger the variance. Then the worse that we would use this SP square as a plug-in estimate for the sigma square. So that's the whole story motivation. And to address this issue, we want to propose a better estimator that will have smaller variance than this SP square does. And we use the Bayesian approach. And to summarize, we introduced the prior of sigma square as a conjugate prior, so that by definition of conjugate prior, this prior and the resulting posterior, which can be obtained by the Bayes rule, will be in the same distribution family. So in here, because we know the distribution of SP square given sigma square based on this chi-square distribution, and then correspondingly, we'll find the conjugate prior as what we call the inverse chi-square. Using this conjugate prior, we would have the posterior still following inverse chi-square with different parameters. And then what we did is to take the expectation of the posterior as the new estimator. And this posterior expectation can be regarded as a weighted sum here, can be regarded as a weighted sum of the estimator, SP square, and the prior mean, S0 square. So you can see that we are combining information from the data and the prior. However, S0 square is what we call the hyperparameter, which is a parameter of the prior distribution. So we have V and S0 square, those two hyperparameters that need to be specified, right? If we know some value here, that's great. Problem solved. We just use that value and we derive the new estimator. But if we don't know this S0 square, what can we do? We have to estimate it in some way. And using the data to estimate hyperparameter is what we call empirical Bayes. So by empirical Bayes, the whole idea is that we would actually try to derive the likelihood of the hyperparameters by integrate out any other parameters in the middle. So in our case, it's sigma square. Integrating out sigma square, we are left with the distribution of our data just given the hyperparameters. And this is what we call the likelihood of the hyperparameters. Then we just try to maximize this hyperparameter likelihood to find estimates for the two hyperparameters. And using those values, we go back to this formula and just use the estimate for S0 square. That's our Bayesian estimator. Okay, so that's the whole idea of using the Bayesian framework. And I want to say that there is a theoretical reason why the Bayesian estimator is good. So I'm not going to give the detail here for this class, but I just want to give you the result. The result is saying that, so let me just put it here. So it's actually some very nice theoretical result about why Bayesian estimator is good. Why is Bayesian estimator good. And when we say good in statistics, we need to specify in what sense. I'm not sure if this is covered in our stats graduate class. I guess 200B, probably you should cover this, but I'm not 100% sure. So anyway, I'll give you the result. And this is something you can look up at Google if you're interested in the proof. So it's saying that if we are interested in estimation, so the goal in our case is to estimate some parameter. Here the parameter is sigma square, right? And how do we evaluate if an estimator is good or not? So let's say we will have an estimator just denoted by sigma square hat. So whenever we put a hat above a parameter, we say it's the estimator of that parameter. Then the criteria, which defines what we mean by good here, is this called risk. Okay, this risk is defined as the expectation of sigma hat square minus sigma square, their difference squared. So it's the expectation of the square difference. And when we write expectation, one question I said in the beginning, I think of this class, of this whole class, right? Maybe the lecture 1 or 2, I said that it's important to think about what random variable or random variables is this expectation with respect to. Okay, about which random variable. So here, the criterion, because we're under the Bayesian framework, under the Bayesian framework, the parameter is random. It follows a prior distribution. The data is also random. It follows the distribution given the parameter value. So here, the expectation is with respect to both. So you are considering both sigma hat square as random and also sigma square. So in other words, you are taking the joint distribution. So this is from the joint distribution of these two. And what do we mean by the joint density? If I write this as the joint density, we can factorize it as the conditional density of the estimator given a particular parameter value and the density of that parameter value. So using the language we learned before, this is our likelihood. This is our prior. Okay, so that's the joint distribution, joint density. And this expectation is taken over this joint density. Okay, and so therefore, we can show that in order to find a way to construct the estimator that minimizes this whole risk, we can show that the estimator is actually the Bayesian estimator. Okay, so we can say that this risk, let me put it down here, is minimized by setting the sigma square hat as the expectation of sigma square given data. This is the known result. And this is what? This is exactly our posterior mean. So this is the theoretical foundation of using the Bayesian estimator if you know the prior. So in other words, here, if this likelihood is known, you know the true model, how the data is generated given the prior, and you know the true prior, how the parameter values are distributed. Then the best estimator you want to have to minimize the risk is actually defined by taking the conditional expectation of the parameter value given the data. And looking here, this is exactly what we did. Because here our data is captured by this SP square. That represents our data. And also speaking of that, this is related to another concept I want to introduce today. And just to know that if you watch the lecture notes I recorded from last year, you will see that every year I teach it differently. I try to add some new things based on how the lecture goes. But here I want to say that this is a concept I also want to introduce from mathematical statistics decision theory. So is this one. So this whole thing is a theoretical result from what we call the decision theory, which is part of the mathematical statistics. But these things, although they are purely based on math, they provide a lot of theoretical justifications for our practices, like this one. This justifies the use of Bayesian estimator if you know the prior. Okay, so speaking of this, right? So in our previous example, let me say, in our previous example, so what I want to say over there is that for the distribution of the sigma square given data, this is the exact definition of posterior. But in that case, we can actually say that this is equal to, this is equal to the distribution of sigma square given SP square. So in other words, here the SP square fully represents our data for describing this posterior. And in this case, we actually give this SP square a name. So we can say the SP square is the sufficient statistic for the parameter sigma square. So you will see this term sufficient statistic in a lot of papers, and roughly speaking, or intuitively speaking, what it means is that if you want to estimate this parameter, then all the necessary information in your data is summarized in SP square. So you just need this SP square, and you don't need other information from the data. You're good to go. Okay, so that's the definition. And mathematically speaking, we can actually say that if we write the likelihood, so basically the likelihood of the parameter, we often need to write down the likelihood based on the data, right? Based on how the data is distributed given the parameter value. And here, we know that the likelihood is usually written in this way. The density of the data given this parameter value. That's how we define the likelihood. But here, what we are trying to say is that, so mathematically, okay, for the sufficient statistic, we can say that this can be written by factorization as the density of data given some sufficient statistic, which I denote by SP square, times the probability, this one, SP square given sigma square. So in other words, so, if I do this directly, I should have the data given, let me see. Right, I should have, so I actually skipped one step. I should make it clear. So this one, I'm saying that this is equal to the data and SP square given sigma square, the joint thing. The reason is that SP square is just a function of the data. So that's why I can put it here. But when I do the factorization, you see that this term should be data given SP square and sigma square. So this multiplies this should be equal to this. That should be correct. Or maybe let me, sorry, I think I might have confused you. So let me just put it here. So I'll try to rewrite it to clarify things. So what I want to say, so let's forget about this. What I want to say is that if I look at this data and statistic given the parameter, this distribution density, originally I should factorize it as data given SP square and sigma square in the conditioning times the density of SP square given sigma square. This is what I should have. But if SP square is sufficient for theta, okay, so when this is sufficient, then the first term becomes the density of data given SP squared times this. Okay, so in other words, what it means is that when you put the sufficient statistic into the conditioning, you no longer need the conditioning on sigma square. And with this, then you can see when I write the likelihood, I just need this term because this is the only term that involves sigma square. I don't need the data anymore. And that's exactly what we did in the previous example. So in the previous example, just as a reminder, look here, when we write it, we are treating this as the likelihood. So the likelihood is purely based on SP square only. We don't use other data. Okay, so that's the sufficient statistic. So in this case, that says the pooled sample variance is the sufficient statistic of the common variance parameter. And for another example, I can tell you, another example is this. So let's say we have x1 to xn. They are IID from a normal distribution with mean, mu, okay, and sigma square. And another straightforward result is that the sufficient statistic of this parameter mu is this xn bar, the average of x1 to xn. So in other words, if you just know the average, you're good to go. That's the only information you need to estimate mu. So that's another example. So what I'm trying to say is to give you this intuitive sense of sufficient statistic. That therefore, in the future, once you encounter this term in some papers, you know what the authors try to say. Okay, do we have questions about the recap of our last lecture and what I just said for the sufficient statistic right now? I think because this is not a mathematical statistics course, I try to give you the intuition behind those terms so that you will see the meaning of it. That's the only purpose. And if some of you here know this concept already, you can also offer your insights if you want. Okay, so before I move on to talk about the next thing, the permutation test, which is very useful for bioinformatics research, for now, I'm going to first talk about this paper I came across yesterday. So this is something I already posted to CCLE under week 3, so you guys can check out later. And I think this is something everybody should try to read. It's very useful. This is a new journal called the Nature Review Methods Primer. I think so. Yeah, Nature Review Methods Primers. So this is a new journal for publishing reviews. And this is a paper called Bayesian Statistics and Modeling, published by multiple statisticians. It's a very long paper. You can see 26 pages, and it covers everything. Almost everything about Bayesian statistics, but it's much shorter than a textbook, and they give you the essence. So that's why I think for those of you who are interested in Bayesian statistics, try to read this, right? Because this is more comprehensive than what we can cover in this class. And later, I think the last part of this class, we will cover the MCMC briefly, which is what will be covered in this article in the latter part. So this article starts with the definition of prior, likelihood, posterior, and talks about how to choose prior and how to evaluate the Bayesian model, see if it's reasonable, and what are the considerations from a practical point of view. So especially this example is actually used throughout this paper called PhD delays. Let's just quickly take a look. This is related to everybody here, right? A lot of you are PhDs. Then you may wonder, will you graduate in time or there will be a delay? So basically the data is about 333 PhDs and in Netherlands and how long it took for them to complete their PhD. So looking at the numbers, the average delay in terms of month, the average delay is 9.97 months, so almost a year. And the minimum, wow, it's minus 31 months, and the maximum is 91 months. So, and the standard deviation is 14 months. So basically they are trying to make a prediction, or they're trying to build this regression model to evaluate the effects of age on the delay. So you see there, this study includes age as a linear term and as a square term in this model. And the parameters of interest include the intercept, the age coefficient, and the age squared coefficient. Okay, so basically the model assumption is that this, we call this error term, epsilon, is normally distributed with mean 0 and an unknown variance denoted by sigma epsilon squared. And we have simplified the statistical model so that, okay, only meant for instructional purposes. So that's the formulation. So if you have taken a linear regression class, maybe your first answer is to run linear regression, right? And estimate intercept and these two coefficients, you're done. But here they're trying to use this example for Bayesian modeling. So for Bayesian modeling, we know that we will assume the parameter to be random. So we need the prior. In this case, I think they focus on this beta age, this parameter, and they try to assume this parameter, beta age, will follow this prior. They assume normal prior. In this case, because the data generation, this distribution is normal. So with this normal likelihood, if you add a normal prior, then they will be conjugate. So the posterior will remain as normal. So things will be easy. So say that this prior is this, then here the mu 0, sigma 0 squared will be referred to as hyperparameters, which we have just seen. Anyway, so a topic I want to briefly point out for this paper is about the informativeness of priors. So let's take a look at this very informative figure right here. So if you guys can see, this is the likelihood in the middle. So in other words, let's think about this is the likelihood of that beta age parameter. So what it means is that this means beta age equals 0, corresponding to this value, then the density of my data would be at this value, this y value. But if I vary my beta age to here, the density of my data would decrease. Okay, so this is describing how the data density changes with the parameter value of beta age. And that's how we define as the likelihood. And then we couple this likelihood with different priors with different levels of informativeness. You can see this is beta age following this prior with mean at 2.5, standard deviation 0.2. So it's a very narrow prior distribution. And we say this is very informative because you can say that it gives us this information that the beta age parameter is likely to take the value 2.5. Right? It's very concentrated on 2.5. So together, this prior and this likelihood will give me this posterior. Posterior is in this green curve. And you can see that as a result, the posterior is also very concentrated and the mean is slightly below 2.5, but it's actually away from the center 0, which is in my likelihood. So in other words, likelihood tells me, my beta age is most likely to be 0. But with this prior, which tells me it should be close to 2.5, together, the posterior tells me the beta age value is likely close to 2.5, but slightly below it. So it's a combination of the results. And if I make this informative prior, you see, it's still at mean, hyperparameter mean 2.5, but the standard deviation is much bigger, 5, right? So in this case, we have a bigger spread, which means that the prior is not so confident. It doesn't say it's very likely to be 2.5. It's although 2.5 is the most likely value, but I have a higher chance to take values far away from it. So then together, you see this posterior, now its spread is bigger than the posterior here because my prior has a bigger uncertainty. And again, the posterior mean is between the likelihood mode here and also the prior mean. So it's in the middle. Okay, now we make the spread even bigger. Now we call this weakly informative. So you see the prior is more spread out. As a result, the posterior, the green curve, is more spread out. Okay, and also one thing to note here is that the prior mean is now changed to 6 from 2.5. So as a result, the posterior mean is also bigger. So furthermore, this one, the spread is the same here. So we say it's weakly informative, but now the prior mean is 0, which is the same as the likelihood mode. Both are 0. So as a result, the posterior is also concentrated on 0 because here the prior information and the likelihood information becomes consistent. But you see the spread or the variance of the posterior is now between the likelihood, it's now smaller than the likelihood. The reason is that even though the weakly informative prior is not that informative, however, it's still better than not knowing anything. So it still helps us shrink the variance a little bit in the posterior compared to the likelihood. So that's why we see that effect in the previous variance estimation example. That is, with the prior added, we have an estimator that has smaller variance, right? We have seen that before. And here it's saying that using the posterior, we can have better confidence about what this parameter value, beta H, may take than just using the likelihood. Okay, finally, this is called a diffuse prior, or sometimes people call it uninformative prior. It's totally flat, which means that the beta H value can take any value here with equal chance, or we can say it's a uniform prior, even though it's not purely uniform, but it looks very uniform here. So in this case, it doesn't help the likelihood in any way, and then the resulting posterior is just in the same shape as the likelihood. Okay, so this is just a graph illustrating the effect of prior on the posterior. And I hope this can give you some intuitive understanding of it. And also, I will go over other things quickly. So it talks about Bayes factors, which we also talked about before. So it's worth looking at it. And furthermore, it talks about this idea called prior predicted distribution. So it's a way to check if the prior actually makes sense. So what does it mean? Let me just quickly go over here. So let's say that here the green curve is the distribution of the data. It's the 333 PhD students delay. We are plotting their delay here in the green density curve. And what are those light blue curves? They were actually the data generated from the prior distribution and the likelihood. Okay, so let's say that you did, for every prior, you pick the prior, you can generate beta H. And given the beta H, you use your linear model, of course, with your estimated error variance, that's sigma epsilon squared, that has to be estimated. You use that model to generate your Y. And then you can plot the resulting Y in the curve. And then you can see, does this curve agree with what I observe here? Okay, if yes or if not, you can say, oh, the prior is reasonable, or if it's not. So for example, let me give you an example. If the data you generated from the prior and the model looks like this curve, it's very far away from this one. Like the two density even look to have different domains, then you would not pick that prior. So this is something just like a post hoc check of the prior specification. And you can read this in detail. So, but I would say this is not using the empirical based approach we said, right? In that case, the hyperparameters will be estimated from data. This is just saying you specify the hyperparameter as some arbitrary values and check whether the results are the data it generated look like the real data. Okay, and also credible interval, recall that we talked about it in lecture 2, I think, right? It's that in that case here, the interval is fixed, but you look at a random parameter and see what the chance that parameter falls in this interval is at 95%, right? So some concepts. And okay, and this is about the likelihood function. If this is something you're not familiar with, the author give you a box, for example. Okay, and this table is about all variants of MCMC. I think it's a quite good summary. And so in the later lecture, we will talk about Metropolis Hastings and MCMC and its special case Gibbs sampler. So we'll talk about those simple things, but this table listed other things. And also variational Bayes is now a very common term used in machine learning and Bayesian statistics. So to put it short, this is just a way to approximate the posterior. So when the posterior is too complicated, we need some approximation to simplify it so we can do a lot of things. And variational Bayes is a way to do the simplification approximation. All right, so these are about MCMC. So I will not talk about them for now, but I would suggest that people try to read this paper if you are interested in knowing more about Bayesian statistics, and this is quite comprehensive. And this is about some software programs. So for example, I know a lot of people use the bugs and also Stan. Those two are very commonly used, and the Stan can be run from R. Okay, so I will stop here, and this one has been posted to Cecily. So coming back to our lecture, the next thing I want to talk about is the permutation test. So now let's say that we have this, recall what we talk about for the t-statistic, t-test, two-sample t-test. Okay, so recall that we are testing the null hypothesis. Maybe let me just write that again. Here is, okay, they follow. They are IID. Okay, I'm just trying to relax the normal assumption and say that they have the common mean mu x and y1 to yn IID with common mean mu y, right? These are our two samples. And the null hypothesis we want to test is mu x equals mu y, while the alternative is mu x doesn't equal mu y. That's the hypothesis we want to test. And then the test statistic, we denote it by T, right? If you recall, it's actually defined as the X bar minus Y bar time, I would say it's actually SP, that pooled variance without a square, times 1 over m plus 1 over n under the root. That's the t-statistic. So the components we need for hypothesis testing, let me quickly summarize. The first is the two hypotheses, null and alternative. We need this. Second, we need a test statistic. And the third component we need is the distribution of the test statistic under the null. So what does it distribute under the null? So under the t-test, we actually know by mathematical statistics, this is following a t distribution with the degrees of freedom as m plus n minus 2. So we know this. And finally, using this null distribution, we compute a p-value, right? So the p-value here is defined as the probability, again, under the null hypothesis. So under the null hypothesis, what is the probability that the absolute value of t would be greater or equal than the observed value, absolute value of the observed value of t? So this t is what we call the realization. I used the term before, or you can consider it as the observed value in our data of this t-statistic. Okay, and here, this probability is calculated as the two tails from the t-distribution, right? That's the whole idea of doing the t-test. This is a summary. But a problem with this test is that what if this null distribution doesn't hold? what if I violate this assumption? So for example, there could be multiple ways to violate the assumption. First is that when I have unequal variances, like we have seen before, if I have unequal variances of here, then this SP square would no longer follow the chi-square distribution. And as a result, this T statistic will not follow the T distribution. So therefore, in this case, the null distribution is just violated. But can we actually solve this problem? And this is one example, and there could be other violations. For example, the normal distribution is violated, and our sample size M and N are very small, so the central limit theorem would not help. So these can be all possibilities. So what if this null distribution of T is unknown? So you don't know, you think this is not right, but you don't know how to derive it. And here, luckily, we have computer to help. So in my opinion, I think the computer development can be regarded as a very powerful replacement for mathematics in statistics. So, this development of the T distribution all relies on mathematics. We need to use our clever minds, our pioneers need to use their clever minds to derive those closed form distribution. By closed form, we mean the analytical form. Then they could simplify the calculation. And people can do this even by looking at the table. But in more complicated situations, this distribution may not have a good analytical form. But the computer can give us a way to generate all possible values of the test statistic under the null. So that solution, this is a common, I would say quite universal solution. It's called a permutation test. So what this does exactly is to generate samples under the null. Generate samples under the null by permutation, actually, in this case. So why does permutation work? Let's say that I pool my samples, two samples together. So I pool them into one set. I have m and plus n numbers, right? I pool them and I just randomly divide. So I will have a set of m numbers and a set of n numbers in each division, right? And I could do this division for how many times? This is a combinatorial problem. I could actually do this for a total of m plus n choose m times, right? I'm just doing the random division. And because I pool those observations into one sample and just randomly divide them into two samples, then I know the resulting two samples are actually from the same distribution. From the same distribution specified by those m plus n numbers, right? And then they share the same mean. So in this case, although I pretend them to be from two conditions, but because of this pooling and random division, these two samples were actually from the same condition. And that is my null. And that's my null hypothesis. So therefore, the whole idea of this permutation test is to generate those null samples. And so in this case, I would say if I denote the resulting samples as, let me say, x1, 1, xm1, and let's say y11 to yn1. This is from the first permutation. I denote the resulting sample by this notation. And then if we go on and I do this for capital B times the capital B's permutation, and I denote that as x1 capital B to xm capital B, y1 capital B to yn capital B. So with those samples, they are all from the null. I could apply the t-statistic formula to these samples, and I can call the resulting value as t1 to t capital B, right? These are what I observe. And then I can say that I will treat those permuted statistic values as the null distribution of my test statistic. So use this set T1, sorry, not one, T1 to TB as values from the null distribution of this test statistic T. Okay, and then finally, to calculate, so we basically replace step 3 by this permutation. So this whole idea is to replace this step 3 in our hypothesis testing. So finally, then step 4, the p-value calculation would be, I look at those null values and see what proportion of them have absolute values greater or equal than the absolute value of my observed test statistic. So in this case, p-value would be defined as 1 over capital B, number of permutations, summation, I let small b from 1 to capital B, and I check using the indicator function whether the absolute value of the B's permuted statistic is greater or equal than the absolute value of my observed statistic. That's it. Okay, so you can see in this whole idea of the permutation test, capital B performs a very crucial role because this number B will determine the resolution of my p-values. So if you imagine the B is 100, then the smallest B p-value I could have is 0. And the next value is 1 over 100, so it's 0.01, right? But if B is 1,000, then the smallest non-zero p-value is 0.001. So that determines the resolution. So in other words, you see here the values, these values could take 0, 1 over B, right? And up to say B over B minus 1 to 1. These are the possible, all the possible values that this can take. And this is the what we call the resolution, p-value resolution. So in this regard, which we'll see very soon, is that the smaller the resolution, the better. Especially this is needed for our multiple testing correction, which I will talk about today. So for this one, if we can afford, right? So the larger B, and B is basically upper bounded by this M plus N, choose M. So that's the biggest permutation you could have. And also you may want to remove the case when the permuted sample is exactly the original sample. So you mean, I know, so for example, there's one division so that the first M is just your x1 to xn, right? And the last n is just your y1 to yn. Then that's your original sample. And you don't want to include that because you know that's not from the null. So therefore you may need to do -1. So with this, then if M and N are very small, then this capital B is also very small. So that's why you can see that this only works well when this M plus N is quite large. Or I should say maybe both M and N are very large, then this permutation makes sense. So that's the limitation. So therefore, this is again consistent with the philosophy I'm saying, right? So think about this normal assumption for the t-test as what we call a parametric assumption. So this parametric assumption is maybe unrealistic, but given the sample size is very small, that's your best bet. So you have to rely on it to do something. But when your sample size is large, you have rich information in your data. Then in this case, you could drop some of those idealistic, unrealistic assumptions and just use the data to make a decision. And this permutation test is such an example. It doesn't require any assumption about the distribution of data. You are just shuffling your observations to create the null. And that will give you the values of the null values of the test statistic. Does that make sense? Okay, so this is the solution people could use if you don't want to assume some assumptions. Does capital I stand for the P? The capital I is the indicator function. So when we say indicator function, we mean that it takes binary values 1 or 0. When it takes value 1, it means that the inequality in the parenthesis holds. Otherwise, it doesn't hold and the value is 0. Okay, so this is it. This is the permutation test. And the next thing, I think I'm going to change the order of my contents a little bit. So you can check the lecture notes I posted to the CCLE homepage, which is a combined, it's a set of the notes we used in past years. It's typed up by some previous students, right? So we're doing that in past years. So you can check that, but I changed some of the material. So that's why I'm not following the order over there, because the original order is that I'm going to talk about normalization as the next thing. But I think it makes more sense for me to continue from here and talk about multiple testing as the next thing. Okay. So for multiple testing, it's a very common problem in bioinformatics because we are not just looking at one hypothesis testing in our study. So, right, so now we are in this so-called high throughput data analysis. By high throughput, that's the biological term. It means that our experiment can measure a lot of things at the same time. For example, next generation sequencing is a high throughput assay. RNA-seq can allow us to measure all the gene expressions in the sample, right? That's high throughput. So therefore, in this case, when we do the differential gene expression analysis, say DE analysis, we were actually doing one test per gene. For each gene, we check if it's differential or not, right? And let's say that in our data set, we have 10 to the 4th genes, 10K genes measure. That's the order of the number of human genes. So if we have those gene measured, then that will be this number of tests, hypothesis tests. Okay, so think about the significance level that alpha equals 0.05 significance level. Think about this. We use as a criterion for calling rejection. What does it mean? It's actually defined as the probability that we reject under the null hypothesis. In other words, the truth is that the null hypothesis is right, but we reject it. So we make a mistake, right? So this is also called type 1 error. These two things are the same. So that 5% is what we control. So basically, there's always a trade-off between what we say the type 1 error and the type 2 error. So the type 2 error, by definition, I'll put it here, is the probability of not rejecting given the alternative is true. So it's the other side. So when the alternative is true, you want to reject, but you didn't reject, right? So therefore, you can see this trade-off. And let me give you another concrete example. So let's say that I have a test statistic, okay? I say this is the test statistic T, and I want to plot its density for different values. So let's say the test statistic under the null hypothesis follows this distribution. Under the null, it follows this distribution. Under the alternative, it follows the right distribution. And I need to decide when to reject. So let's say that my threshold is at this small t, which means that I reject if this big T, the test statistic, is greater or equal than a small t. So in other words, I reject the right-hand side and I don't reject the left-hand side. But then you can see what's the type 1 error. The type 1 error is actually the area under the left density above this small t. So it will be this thing. That's the type 1 error, right? Because here the test statistic is actually from the null, but because it's greater than t, I reject the null. So then the type 1 error in this case would be this shaded area. Type 2 error on the other side, on the other hand, is the case when my test statistic is not bigger than t on the left-hand side, but it's from the alternative distribution. So the type 2 error would be, let me see, would be this part. That's the type 2 error. So this shaded area in the other direction. So you see that the type 1 error, type 2 error, they are hand in hand. In other words, there are trade-offs. So if I move this t, threshold t to the right, you see what happens is that type 1 error would go down, type 2 error would go up. If I shift the t to the left-hand side, it's reversed. Type 1 error go up, type 2 error go down. Right? So the thing is that as long as my test statistic has overlapping distributions under the two hypotheses, I would always face this trade-off. I cannot give a perfect result. Does that make sense to everybody? Okay, so in another case, this type 1 error is the probability that one test is a false, let me say, using our language, one test is a false positive. By false positive, we mean that the gene is not DE, but we call it DE. Okay, so alpha by type 1 error is the probability that a non-DE gene is called DE. So in other words, we say it's false positive because in our case, calling it DE is a positive, but it's false. So let's say that if we have just one test to do, then the chance we're making a type 1 error is alpha, right? If alpha is 5%, it's 5%. How about if we have 10,000 genes? So therefore, you see the expected number of, I call this FP, of false positive genes is actually what? False positives is actually the number of non-DE genes times alpha. That would be the expected number. And since we believe that the majority of genes are non-DE, only a small proportion is DE. So therefore, let's say if out of the 10K, how about we say 8,000 is non-DE? And if we multiply this number for 5% with 5%, what do I get? 400. So in this case, you would expect to have 400 false discoveries, false positives using the alpha as 5%, right? Wouldn't this be something to worry about? Yes. So that's why we face this problem. The alpha 5% that seems to be small enough for one test now becomes too big for so many tests, right? So we need multiple, we'll call this multiple testing correction. This is the motivation of doing this. Otherwise, we're afraid that we may have too many false positives. Okay, so related to this, there are two criteria that has been proposed. So the first criterion, so we need a new criteria other than the type 1 error or significance level. That's not satisfactory. The first criterion is called family-wise error rate. Which is short as FWER. So in this family-wise error rate, what we aim to control is the total number of false positives. Okay, so let's say that we define V as the number of false positives. In other words, the number of non-DE genes that were rejected. So in this case, the family-wise error rate is defined as the probability that this V is greater or equal than 1. That means what's the chance that we have at least one false positive? So no matter V being 1 or 2 or 100, they are all counted towards this probability. Okay, so to control this, what do we do? So this means that we are going to examine every gene and see if that gene is a false positive, right? So basically, we are going to say that let's say we have P genes. Let me see. Yeah, I'll just use that. So let's say we have a total of P genes. Then we just check this probability of this union event. Let's say we let J go from 1 to P, and we check the union whether gene J is false positive. So, right, so if one of these events happen, this union would happen, and then that satisfies this, right? That's the whole logic. And now we are going to use a very common inequality in probability. That is, the probability of the union is upper bounded or less or equal than the sum of the probability of individual events. So we're going to use that. Then this union probability is less or equal than the probability, less or equal than the sum J from 1 to P, the probability that gene J is FP, is false positive. Okay, and what's that probability? Do we know? What's this probability that the gene J is FP? That means if the gene J is non-DE, but we call it the alpha. Great, thanks for the answer. Yeah, so that probability is alpha. So actually we should say less or equal than alpha to be more exact, right? So because here we are setting the significance level to alpha. So we try to control that under alpha. So because it's the alpha, we sum it up, the same thing up for P times. So it's actually P times alpha. Okay, we upper bound the family-wise error rate. So this could be a very loose upper bound because this could be much larger than that. That is always valid. So if we want to bound this family-wise error rate, so to set family-wise error rate to say under 5%. If that's the thing we want to control, then it is sufficient. A sufficient condition is to set this alpha less or equal than 5% divided by P, right? So if we set a significance level to be under this, as a result, by this inequality, the family-wise error rate will be under 5%, okay? And this is what we called Bonferroni correction. So Bonferroni correction is very simple. What it does is that to set significance level to the family-wise error rate, upper bound you desire, divided by the number of tests. So you are no longer controlling significance level to 5%. Instead, you're controlling it to 5% divided by the number of tests. So this is very conservative, but it works. It can actually ensure that you will not have too many false positives, right? Because the chance of having any false positive is under 5%, which is very rare. But the problem is that being too conservative. Too conservative. And you can see that, especially for our gene expression analysis, 5% over 10K is what? So it's actually 5 times 10 to the negative 6. That's what we will have. So you may not have any p-value under this. So if you have no p-values under this, so if that's the case, all the p-values are greater than this, then you will have no rejection, which means that you will identify no DE genes. And to biologists, this is unacceptable. It means that I cannot find anything from my data. What's the meaning of generating this data, right? And their data are very precious. So that's why people have to propose a new criteria to replace this family-wise error rate, which is good, but too conservative. All right, so, and also now you see for the permutation test, if you don't permute enough, you will never get a p-value this small, right? Then no rejection. All right, the second criterion, which is the most popular criterion people use nowadays, is called the false discovery rate, short as FDR. Okay, this criterion was proposed in the Benjamini Hochberg paper in 1995. So this is the paper that has been cited the most number of times, I think, among all the statistics papers, because this criterion has been so popular in biomedical data analysis. Almost every paper now, when they do a multiple testing, they would follow the FDR. Okay, so the FDR is not based on this family-wise error rate. It looks at different perspectives. So for biologists, if you think about your data analysis, what you are mostly interested in is that among the DE genes I caught, what percentage is false positive? So that percentage matters. Let's say if I find 100 DE genes and among the 100, 5 is false positive, 95 is correct, then I may be happy, right? So that percentage is more important than simply this probability of having any false positives. So that's the motivation of the FDR. So besides the V, let's say that we have this R. So recall V is the number of false positives. And let's say R is the number of rejections. Okay, the number of DE genes you caught. So basically V is a proportion of R. So basically I will have R equals to V plus the number of true positives, the ones you caught correct. So the first criteria defined here is this V over R, the ratio of false positives over among all the positives, among all the rejections. Yeah. So in this case, this is called false discovery proportion, short as FDP. This is the motivation. So hopefully among my R, V is a small proportion. But think about statistics, right? We care about randomness in our data. Then do we have randomness here? Yes, we do. There are two layers of randomness. First, our data is random. And second, given the data is random, when we add the rejection criteria. So if the rejection criteria is fixed, right? We just reject based on this rule. There's no more randomness introduced by the rejection. Then all the randomness come from the data, which means that the number R and the number V would change if you collect the data for another time. So following the same experimental procedure, I get a sample, you get a sample, we apply the same say differential expression method, then my V and R and your V and R will be two different sets of numbers, right? So our ratios will also be different. So therefore, in statistics, we do not only care about one particular data set, or we say one particular realization. We care about how the procedure would work in general on all the possible data sets. So to talk about that general, we talk about expectation. So if we take the expectation of this random ratio, and expectation is with respect to the data generation, we call this FDR. So in other words, FDR is a criterion that is the expectation of FDP. So therefore, the criterion is no longer random because the expectation takes care of all the randomness. And think about the family-wise error rate. It's not random either because this is a probability, right? We consider V, V is random, right? The number of false positives we can make can change from one experiment to another experiment. But we're looking at the average, which is the average case of making at least one false positive. Okay, so how do we control this FDR? So actually, you can think about one issue we may need to address is that this FDP is a ratio, right? How do we set this ratio when we don't make any rejections when R equals 0? So we need to make that exception. So this is actually set to be exactly to be, let me say that okay, so exactly is FDR is defined as, or I should say this, FDP is defined as V over R if R is greater than 0, when there's one rejection, and otherwise, if R is 0, it's defined as 0. So I just talk about that dividing 0 issue we need to consider here. And then FDR is the expectation of FDP. Okay, so that's the definition. And to control the FDR, this seems to be so difficult, right? If you think about the problem, how do we know the expectation? I don't know the exact distribution by data generation. How can I calculate this expectation? That seems to be too difficult. But again, our bright, clever minds gave us a very good answer, which is the Benjamini-Hochberg algorithm procedure. So that procedure makes this controlling of FDR possible, which is actually very simple. Let me quickly give you the procedure and stop here for today. So regarding the intuitive justification, we'll come back to that next time. So there are just 2 steps, okay? The first step is that it will basically it will use the p-values. So it starts with the p-values for all the genes. Okay, so I will denote it by maybe P1 to PP. Recall that I have P genes, P tests. So the p-values. You have those p-values calculated already. And the first step in the BH procedure is to sort the p-values from the smallest to the biggest. So with the sorting, I will write it as parentheses. So P1 is less or equal than P2, less or equal than PP. So the smallest p-value may correspond to any one of those, but I just denote it by parentheses to mean it's the smallest one. And this is the biggest one. So with the sorting, the next thing is to compare each PI with a threshold. And the threshold is denoted by, I'm still trying to use the, say, 5% as our target FDR, okay? So I will compare that against the 5% target times this I, the ith p-value order divided by p. So I will compare this p-value with that, and then I will pick, finally, I will pick the largest order k such that I would have all the p-values, sorted p-values under k less or equal than this 5% threshold times I over p for I less or equal than k. So in other words, I move my order and check whether this p-value is smaller or equal than this threshold. If so, I move to the next p-value and do the comparison. And I move and move until this is no longer satisfied. Then I go back to the previous one and set that to be the k. Okay, so it's a step-by-step comparison. And I would reject. So for finally, with this k picked, I would reject the hypothesis, the null hypothesis. I will reject the nulls of this first k p-values. So all the p-values before k after the sorting will have their null hypothesis rejected. So this is the BH procedure. And if we do a very quick comparison of the BH against the Bonferroni, then you can see the difference. So let's say that we have the PI as the ith order p-value. Now under the Bonferroni, what we will do is to compare PI against this 5% over p. It's this threshold we are going to compare against every p-value. Well, under the BH, we are going to compare it against the 5% divided by p times I. So then you can see this I, when I equals 1, for the smallest p-value, the two thresholds are the same. But as I increases, the BH procedure will increase the threshold. So let I go from 1 to p. So finally, it will become 5% when I equals p, while this Bonferroni will stay the same. So that's why you will have more rejection under the BH procedure, right? By the threshold. So that's why we're saying that even though we start with the same p-values, though using the two procedure, we will have different number of rejections. And the fundamental reason is that we use different criteria. Here, we are trying to satisfy the family-wise error rate control, while here, we are just trying to satisfy the FDR control. So by changing the criterion, statistical criterion, we will have different rejections. So scientifically, our data don't change and our p-values are the same, but statistically, by changing our criterion, in other words, our analytical expectation, we will have different analytical results. So I feel like this can be an example to show you that statistical analysis can be subjective again. So you design the criterion and you justify why the criterion is reasonable, and that will give you the result. Does that make sense to people? So I did explain why this procedure worked, but this is just the procedure. So it's very simple, and you just sort your p-values. That's it, and compare it to a changing threshold. Okay, maybe I'll just quickly wrap up by using a graphical illustration. So let's say this is your I, right? The order, and I goes from 1 to P. And let's say the y-axis is the corresponding order p-value pi. So say you want to target FDR at the 5%. This is the 5%, right? Or maybe let me do 0, 1 here. Okay, and then you just find the corresponding line as a straight line, 5%. So that would be the straight line. Okay, that line gives you 5% divided by P times I. Okay, and then your P values would be somewhere here. P value, the first one, second one, and you may find that, okay, gradually, then after that, the P value goes up. If that's the case, you are going to reject the first 4. So just find whenever the p-value cross the line, and then you reject anything before that. So that's the basic idea of the BH procedure. Okay, so I think I'll stop here, and next time we'll come back and talk more about this FDR control thing. And so for today, yeah.
Okay, I have a question.
Yeah, sure.
So I understand this procedure is different for Bonferroni and BH methods. So, for example, if we are doing a like epigenomic analysis, and then we use Bonferroni, for example, as our method 1 to to confirm our results is valid or not, and then we found like 10 genes are highly related to our outcome. But for the BH, actually we have more rejections. So we have like 20 genes that is highly related to our outcome. So how would we interpret our results biologically? Does that mean like if we use Bonferroni, then we just filter out those 10 additional genes? I don't know how to
okay, so you interpret the results, right? So let's say that for both you are setting 5% as the threshold. Then for the 20 genes you found from BH, from Benjamin Hochberg, then you can say that, oh, those 20 genes satisfy that I expect 5% of them is a false positive. So in other words, here I would expect that I expect to have 1 false positive among my 20. So that's what I would tell the biologist. And okay, if you use the Bonferroni, you would say, oh, given the 10 genes, I would expect that there's only 5% of chance I have 1 false positive. So you see, that's the difference. So one is expected to have 1 positive. One is that you expect to have 5% of chance to have 1 false positive, which means that 95% of chance my 10 genes are perfect.
Okay, understood. Thank you.
Thank you for that's a wonderful question, right? We need to tell them what it means, because you don't want to use the jargons when you talk to biologists. Thank you for the question. All right, so I will assign the first homework today, which you will have 2 weeks to do it, so plenty of time. And also we will give you the final project data set next week. So if you want to start early, you can do so. And also if you want to find a group partner to form a group of 2 people, you can start doing that. And you can also work by yourself if you prefer. Okay, so I'll see you on next Monday at 2:30 p.m. Bye. Okay, we have some questions, or thank you. Yeah, thank you all. See you next Monday.
Quick question. Is office hours the same Zoom link or is it in?
The same Zoom link. Yes, use
Okay.
the office hours. Okay.
Okay, thank you. Bye.